Quay xem cái đấy. Đấy. Không em để tu tí phụ.
Did you finish?
One, shy two, until shy two, I solved shy case. Hi everyone. Right.
Ahí tío, voló y tanto, te solo, ni voló y tanto, al solo y tanto. Dando ni, pues sé que no.
Oh, is that a message?
Kaya bicara sa movie, what is that?
I think. So the question is, help me. So is there any error in the form of guidance?
I haven't checked that yet.
No, it's okay, let's see that. So there is a current that's coming out, right, like this?
Two conducting plates occupying y equals 0 and y equals a.
So that's y equal to 0, y equal to a.
And then it says the positive and negative charge density is flowing in the positive and negative direction.
So that's z, so probably x as well. So this is z, let's say. X. Right, okay, so. For the magnetic field, if I, tell me again?
Well, the magnetic field is set in the z direction.
Z, so, okay, so that means the current is in this direction, that's all, right? So, help me again, sorry. Current, if it was this way. Flowing in this direction, so I will have magnetic field.
Look at the other way.
Do you want
Look inside.
Oh, yeah. Z that.
Magnetic field
Yeah,
and y.
Yeah.
The question, one more question, right?
Oh, yeah,
Was it due today or Thursday?
No, it's due to,
yeah.
understand.
No, I think the point is it correct or not, the question?
Oh, I guess it's right.
Is it correct? Okay, well, okay. So. Flowing in the positive z direction, oh, so the current is flowing inside. Yeah, I think. So current is, so this is the current I. Inside. And. So going in. So I have a magnetic field going down.
Which is,
It's going down.
Oh, yeah, that is a problem, right? Negative charge density.
yeah, it should be in the X,
Flowing in the
X direction, right? Not the Z.
Yeah, yeah. No, you're correct, yeah. Correct. Yeah. That's,
So do we just change
yeah, change that.
the V vector to positive X or negative?
Okay, let me fix this. Let me. Okay. So we have
Two plates.
two plates and let's,
Y direction is from left to right. I guess.
first let me choose the current to be in the see that, so let's say the current is coming out. So that fixes my z direction,
Mhm.
and that's my x, and that's my y.
No, your Y is the other one.
Huh? No, but if this is z, I am supposed to be having x and y, right?
No, but your plates are set to Y equal to 0 and Y. equal
Oh,
to
I
A.
see, I see, I see. So,
So it changes the Y direction.
so then I am supposed to have this y thing,
Mhm.
and that forces me to have this as x. And this is then z, correct?
Alright.
Reasonable? Okay. Now let me read again.
That's
So it's constantly flowing in the opposite directions, z. So that's,
So, and the other side would be going in the positive.
so you would like the magnetic field to be in the x direction, correct?
Yeah.
Right. And if this is the rest, then it becomes pure electricity. So B should be in the x direction. Is that the point here?
Mhm.
Thank you. So this is really now. Yeah, Christian, so this one is struggle there, the first step.
Everything else is right.
X back, right?
Mhm.
Okay, so the typo is in this. Typo. Oh, it's correct.
Mhm.
What was the question?
It's in the
No,
Z
in the
hat, there
question
is
it says-
the Z hat, but it should be X hat. Otherwise, current and magnetic field. will go in the same direction.
Thank you very much. Yeah, okay. Yeah. I have a comment on the homework you all submitted on homework 3. Some of you are still using the component notation tx, ty, tz. I don't mind it, but I did take away points for those who did not complete it using that. And my point is that I'll be giving this in the exam. You may not be able to do this in the exam. It might be too tedious for you to do that or employ that in the exam. Is that clear what I'm saying?
To use what?
So suppose I ask you to do, like say, I think phrase of ET, right?
Mhm.
I suppose I ask you to calculate this. Perfectly fine if you do EX, EY, EZ, so E1, E2, E3, all the components you put in. There's absolutely nothing wrong in that. It's correct, very correct. But it's very tedious. And
I don't mind, you might say that I don't care, I am ready to spend the time, but I will be asking this in the exam. And it may not be economical time-wise for you to do that, try that at that time. Again, so what I say is that pick up the dialectic notation. It will be useful in the, so this is a, what do you say? Coursework, so this is the time to learn it, so. Take help from me, take from others to go through. So, otherwise, as far as you get it done, I don't mind. And I feel that if you try that in the exam, it might take away all the time and you won't have any other time for other questions, so. It's not significant, it's a notation, yeah, usually. Anything new is, when you can do it the other way, why do it? That's the first thing that comes about, but. I think it will be useful, in the course, okay, so that's that recommendation. And like, we have an exam next week, I know that, there will be a couple of questions on dialectic notation, so pick it up.
Up to what?
Oh, what
day?
are we going to have for the exam? Everything until homework 5, so the homework 5 has been posted. The homework 4 is due Thursday, so February 16, and homework 5, I'm making it due on the day of the exam. It's not the best because you don't get any feedback for the
No, if we're doing it.
mistakes you make, but you'll have it anyway.
So homework 5 will be in the exam.
Yes, homework 5 will be in the exam, and it is about special relativity. Many of us have done special relativity here and there. Math, have you done relativity in any form before?
Like Lorentz
Like
contraction.
contraction and time dilation. And in this first week, we'll be mostly dealing with that. So, and of course, we will go beyond what you probably have seen in undergraduate physics. We'll do more than that. But this one should be straightforward. So I think I can go ahead and do it in the exam. So that's trying to say.
What are since I'm kind of new to your class, I guess, what's the usual format of the exam?
Oh,
And are there cheat sheets or whatever?
if you take the homework problems, like studying for the homework alone is not necessary, not sufficient for the exam, but if you work on the homework on your own carefully, then it will be, that will be the style of problems, but much shorter.
Okay.
Like it won't be long because we won't have the time to do that. And the old exams are available on the website,
Yeah.
the course webpage, so check it out. That's
Oh yeah,
way to.
I can do that.
Also be careful in making judgments there, because sometimes I put a take-home part of the exam, which is usually long. So whenever there is a long thing that I want
Experiments to take home.
so I make it take home. So usually there is a part which is take home and part which is in class.
Mhm.
The in class usually, if you know the problem, it should take only 5 or 10 minutes. Most often you struggle with the problem itself, so probably 15 minutes, so about 4 problems in an hour. So that's how I think.
Is
This time I don't plan to have any take home part to the midterms. It will be all in class. So, or at least that's the plan I have. Yeah, it might change. Yes.
and are there any cheat sheets we're allowed to use, like we're allowed to write down equations and such?
Good point.
Because I know some of my classes, there's so many equations we have to.
Let's see. What are the cheat sheets you will like to have?
Well, I'm used to like you just have a front and back and you can write equations and such on it. Like for example, D is equal to epsilon.
Yeah, I'm thinking.
And give us the equations that we need.
Yeah, I know. And district efficient, but I'm wondering whether to allow it or not.
If you think we'll be cheating too much, you can do like you can make a short one, I guess, for us, or we can do it ourselves. It's up to you.
No, I'm wondering, can I make it open notebook? So,
Oh,
not just a
open
cheat
notes.
sheet, I can make it, give me its,
Oh, usually that would be more difficult.
Well,
no,
it
I
depends
was-
on the person.
yeah, I was thinking without making the exam difficult because of this constraint. Do you, like I roughly have, what I know, like it's going to be dyadic notation because I've got out that and, yeah, let's keep it close notes, just keep it simple, okay,
And not cheat sheet, right?
and what are the cheat sheets you want? I'm curious.
Well, like, I'll show you.
No, I know what you mean by a cheat sheet, but I'm saying,
Oh, like what I would write on it?
like, what are the equations you would like in this exam?
So, what's my notes?
Those you wanted the questions.
Yeah, those that are helpful for the question.
We write the whole.
Like, for example,
Maxwell's equation.
yeah, for example, Maxwell's equations, definition of a delta equation, maybe.
So here is how I get it. Can you all collaborate and come up with an handwritten cheat sheet? And that's on for all of you. And pass it through me.
Would we all have the same one?
Yeah,
Okay.
like, but you can,
But we do it.
yeah, you guys collaborate and write on it, and then I edit it. I come with it, let's like this.
Wow.
So
Yes, sir.
Professor Mark used to give a whole sheet bunch of formulas in the exam, every exam.
Is that what you want?
I'm not sure if he,
Yeah, I know what you mean, but I'm just wondering what are the things that will be useful in this exam, like, and,
So other than that, there will be a special integration in the.
yes.
Well, one equation, I guess, could be partial of u, partial of t plus the gradients dot with s plus j dot with e equals 0. And that would show, like, flux of electromagnetic energy and stuff like that.
How about this? Can I suggest the following? No cheat sheet, but if you ask me anything
Oh, you'll
during
tell
the
us.
exam, I'll tell it to you. And I'll put it on the board. But anything doesn't mean the answer. But something like, for example, this formula that I want this integral.
Or like, what's the total energy stored in plates? You will tell us it's equal to half CV squared.
Yes, that I can tell you, something like that, something which I feel is not going to hurt the assessment of the question. I'll tell it to everyone, I'll write it on the board. Is that reasonable?
Yeah.
Right, okay.
Or like, would you tell us what the trace, remind us what, or like, in matrix form, what a trace of a tensor would look like?
Okay.
I did that.
See, the challenge here is that I don't know what I'll say yes and no.
Yeah,
This
yeah.
question I can always say, yes, I will tell it to you.
I might
But
make one
during the
just,
exam, I might just say that, no, I cannot tell it to you, and then.
I might make one just like, for review, because honestly, it's like good way to review, but, and then I might show it to you and see what you think.
Sure, okay, so let's go with that, okay. So you're going to make an equation sheet and then, if I like it enough, I'll give it to everyone, is that? If,
Sure, I mean, other people can help too,
yeah,
and not just.
okay, reasonable? Yeah. And I can also say no.
Yeah. If you say no, then it's just me.
Yeah, then you just, I don't enjoy memorization so much, I don't want to encourage that, that's. why-
I'm not good at memorization. which is
Yeah, I
why
would
use-
allow it, but, yeah, most probably I'll allow it. Okay,
Usually we don't use cheat sheet, we just fail and then.
That is an option.
so Professor, why you are not considering the take home anymore? Like,
Yeah.
oh, no, okay,
That
so
was
this,
good.
no, I'm not against take home at all, or not, I like take home. But this is the first exam we are having in this class.
Okay, first, just for first.
In this, so I'm not saying that, so usually how it happens is that take home takes away a bit of assessment becomes harder.
Okay.
Like, I don't like it, but a good part of my job here is to assess you, put some hierarchy, 1, 2, 3, like whatever that is, so I have to do that. And it's easy to do that using some simple questions, which if you don't know, then okay, you get a B. So I don't like that, but that's what I have to do. And sometimes when there are only 2 students or so, then I just don't do it, and I just do it the exam. And also take home exam and it's done. But this is a relatively bigger class, so I'm going to begin with that. And if you guys all do perfectly nice, then we don't have to worry about any assessment, then we just have to take.
But if we all fail.
Yeah, then, so that's the tricky part. So when everyone, the response is not sufficient, then I have to take that all through. I have to justify the grade I am giving. If I'm giving A to everyone, then it's easy. We just learn and move on. Did I answer it? So, yeah. So. Yeah. So the bad part of the, or the uninteresting part of the course, I suppose.
Still important though.
Yeah. Important because of the grades.
I wonder what school would be like though, if the grade system was very different, like.
Shouldn't it be like that?
Hmm?
Shouldn't it be like that?
Well, yeah, like grades, I mean, grades are part of the reason why some students hate school, but it's also part of the reason why some students won't
Stop working.
work yet in school.
Yeah, it can be. Yeah, it's a good discussion to have. Yes, okay, so. Let's. Do the stress on a medium that we worked on. Basically, we introduced all the equation there, but still it was mostly static scenarios we considered. We could have dealt dynamical scenarios also to a certain extent there, because there was a time derivative of the like the equation we dealt with was just right. For example, energy density was the change in energy at a certain point is equal to the divergence of the flux of energy plus the energy you lose into the electric field. Like, so that's it. So there is this time dependence, but if you notice, most of the examples we did, the time derivative was going to be zero. Right, so I didn't really emphasize on it, mostly to keep the discussion simple. That was the only reason one could talk about that, one could construct such example, but we kept it low profile. But now let's actually at least talk about one significant result of Maxwell's equation, and that is that electromagnetism or light is an electromagnetic wave, or the existence of electromagnetic wave, which has a speed that is a universal constant. It does not depend by universal constant. It means that it does not depend on any properties of a medium. It doesn't depend on the property of whether it is a wood or a metal or anything. It just is a constant, and the expectation is that in any galaxy you go, these equations will remain the same and speed of light will be exactly the same. And to our understanding and to our observations do verify these things. So let's go back to Maxwell's equation and then get the speed of light in a very quick manner, and then see how Lorentz transformation comes about using that. So again, Maxwell's equation. So. Divergence of electric field. All position and time dependent, that's equal to rho over epsilon naught, right? Charge density and electric field. Divergence of the magnetic field is 0. There is no north pole, no magnetic monopoles if you want. And del cross E, the curl of the electric field is equal to negative time derivative of the magnetic field, and del cross H equal to let me replace this H with P over mu naught. Notice when we were writing the Maxwell's equations earlier, we explicitly allowed a medium to be there. In general, this is epsilon. P is equal to mu. That's the property of a medium, and we immediately say that if it is a vacuum, this becomes H. So at this point, we want to work with the vacuum properties. We are in vacuum, but we still allow charge, charge density and current density be there. So that could be distributed charges and currents around. Yes, Krishna.
Why did you put a
Arrow?
yeah above the E and the U or the epsilon U?
This is like so for example, why is that an arrow? So if you have a
It's like in case there's multiple mediums or
not multiple
Simulation.
mediums, so let's say, so this is a signature of the fact that if you have a material, so let's say you have a capacitor,
oh, and it's different among different
directions.
Yeah.
So for example, if you have a capacitor, you exert an electric field or you provide an electric field, the expectation is that the polarization will be in this direction. Right? Positive charges will get pulled this way and negative charges. But that's not necessary. You want to think of materials where you exert an electric field this way, but it polarizes in the other way. Right? Non-trivial geometries, right? So in general, what you're saying is that the polarization in the X direction can get contributions from XX. So this is EX, EY, EZ. Think of it as a matrix. So this is the component that gives you the X component when an X component is allowed. But you can also have a polarization in the X direction when the electric field is in the Y direction. A non-trivial scenario, very not very common, but and in general, you can have the complete YX, YY. Oops, that should answer that question. You see this somewhere else also, I think, in moment of inertia, like that's the tensor that you see, or even force, right? It is not necessary that when you have a stress or a strain, especially, right? If if I exert a force, something gets pulled. If it's a rubber band, it is usually if you, there is an elastic material, you pull it in the Z direction, it gets stretched in the Z direction. But that's not necessarily true. You can have a stretch in the X direction when you're pulling it in the Z direction, and then you have these quantities coming in, right? So the same idea in that, but vacuum is isotropic. And so this immediately loses that tensor properties. Okay. As we said, there is also the Lorentz force that is in there, but today's discussion we won't need it, so I won't get in. Let's manipulate these equations. Let's take the curl of the third equation. We have curl and curl are the derivatives with position and time commute. So I can write this as curl of B. But the curl of B, substitute using the fourth equation there. And what I have is d by dt of epsilon naught mu naught electric field, and I have a mu naught times J also. Okay. There is a curl of a curve. There's a vector identity associated with that. Use that in here. So we have the gradient of the divergence of the electric field minus the Laplacian. That's a vector identity. Use your divergence expression in there and rewrite so that all the electric field comes onto the left side and all the sources goes to the right side. So you have yeah, so it is square b square epsilon. That's your two terms with time derivative and the gradient. And what is on the right side now is it's all sources. I bring this to the right hand side, so that's minus of 1 over epsilon naught times gradient of rho. That's by substituting the rho in there. And I have the time derivative of J, right? It's minus of mu naught times time derivative J. Let's think of a situation where you have these charges and currents, but of course we never talk about the electric field on a charge or on a current, right? We want to talk about the electric field in a region where the charges are not there. So let's talk about regions where rho is equal to 0 and J is equal to 0. That's not an assumption. We are just saying that we are outside the region rho and J. So in those regions alone, like of course, rho will create your electric field, but in those regions, what we have is epsilon naught, mu naught, field is equal to 0. More explicitly, we have. Oh, remember how much is mu naught epsilon naught equal to? 1 over c squared, very good. And how much is c equal to?
3 times 10 to the 8 meters per second.
3 times 10 raised to 8, so that's 2 single digits. So but since I think a decade or so, speed of light has been fixed as an integer, right? It has been chosen to be an integer, and every other quantity they have changed it to measure. They changed the way digits accordingly. So speed of light now is 299,792,458. So it's complete. That's not an approximation. So that's a choice. Remember, between many constants, you can pick one of them, and then everything else is defined in terms of that. So that's speed of light, or some speed at this point, right? Since we haven't talked about this c yet, so these constants imply that there is a unit or there's a quantity with the units of speed speed, and this can be written as 1 over c squared by dt squared. And just to clarify this better, this is like this. And the electric field is dependent on x, y, z, and t is equal to 0. All right. And this is a well-known equation. What is that equation known as? This partial differential equation has a meaning.
The number
Oh,
square.
yeah, but it's simpler, more physically speaking. What does it imply? Like it says that the electric field has to be having, what's the solution to this? How about it? What's the
Wave.
solution to this electric
Wave.
Yes, so it's a wave. And what is a wave? What's the solution? Yes, that's correct. So this is called a wave equation. Very good. So this is a wave equation. This immediately tells us that electric field are waves, right? But not necessarily monochromatic waves. We always imagine sine waves as sine and cosine waves. But what's the most general solution to this equation? Sum of sine and cosine.
And
That's a very good answer,
Exponential.
because everything can be written as a sine and
should be
cosine.
exponential
Correct.
too.
Huh?
Exponential and sine cosine.
But that's the same as what Abdullah is saying, that sine and cosine, but that's correct. Most of the functions can be written as a sum of sine and cosine. In fact, every function can be written as an expansion in terms of sine and cosine, but not every function is a solution to the equation, right? So what should that?
And it should have hyperbolic sine and cosine too.
Hyperbolic sine and cosine of?
It depends on the constant we are choosing.
What's the constant? K. K, there's a K.
It should be positive and negative. One of them should be sine cosine, the other one should be hyperbolic function.
No, that's too specific. That's one solution.
Isn't just
More.
sine,
Sine is a solution. Okay, how about
well, like sine,
let's begin with give me a solution. Okay, how about that? So give me a solution of E here. Okay, so if you allow me to write E of RP. Let's pick the direction to be some Z hat, so the direction is gone. Right, give me a solution, sine of, right? So you need a unit, so E naught times sine of, what is it? It'll give me this, right? Argument. Yeah.
Omega, I think.
There's no omega there. There's no omega. But if you want, you can,
Is there an exponential?
no, I'm saying, give me a solution that's satisfied. Sine and cosine are good, but to get you the most general solution, I'm at least going to write that.
And pi is
Pi?
and pi, 2 and pi.
3 and pi.
Something
Okay,
like
let's see, right,
Sine of x.
time.
yeah, x. T. No, I have. Some counts, yeah, so that's what we're saying. Okay, how about this? Have omega and k's for you.
Okay.
Then what?
Kx,
Kx,
ky, kc.
k dotted x maybe,
Yes.
yeah, then
Plus omega t.
plus or minus, maybe. Plus is also good,
Oh,
right? Where at this point, k and omega. Right, but is there a condition on k and omega? Like there is no k and omega in that. Right, so where is this k and omega?
K is equal to n pi.
No,
so we have to solve for k, right?
so here's the point, so here, these are any k's and any omegas as far as they satisfy k dotted with k minus omega square is equal to 0. Why did that happen? Right, maybe that is a c, right? Omega square c square. Okay, so this is 1 over lambda, right? So this is c square. Correct? No. Yeah, c cancels out and that's, yeah, third dimensional, that's correct. Okay, so let's see, okay, so you don't believe that, so let's say that I grant you that this is a solution, but let's verify that. But I'm saying this is not the most, this is the very specific solution. It's much more general, the wave equation, so I'm motivating you into that, but let's substitute this, okay? So time derivative of E, 1 over C of E. Everything remains the same, E naught, because of this time derivative, that is a plus or minus omega that comes in, correct? So that is omega over C plus or minus. And actually, I'll just write it as plus or minus omega over C and E. Is that correct? Oh, no, cosine, sorry. How about this? C square is omega square, C square times E. Is that correct? Maybe minus. Is that correct? If I take this two derivatives of this, sine becomes a cosine again becomes a sine. And it gives me, the time derivative gives me an omega out, right, with a negative sign. Agree? With me? Do the same thing with d square by dx square of E. This will give me a minus kx square times E. Agreed? Like I take the derivative with respect to x, only the kx comes out, that's the minus kx. If I do all this in here, you are telling me that this is a solution, right? As of now, it is not a solution because if I substitute it in there, I get minus omega square c square, right? Plus kx square, plus ky square, plus kz square, times electric field. Why should this be 0? It's not 0. Right? I evaluate this, substitute it on the left hand side. So that's left hand side is equal to this. That's not 0, right?
Unless k squared is equal to.
Unless this is equal to 0. So this is equal to 0 only if so. Now you have to come up with a condition that when you wrote this, if you require that this is the case, right? This is equal to 0, then this is equal to 0. Right? That's equal to 0. not always. But why this? Well, then you say that, oh, where did this come from? And if you pay some attention now, is it necessary that this should be sine? No, right? What else could it be?
Cosine.
Cosine, okay, I give that. Anything else? Can you be more?
Exponential.
Exponential, okay, exponential, tangent, yeah, tangent. I say any function.
Yeah.
Give any function and that's satisfied. Because it didn't care, right? This was any function. Who cares? What was this? So, right, this just kept the electric field intact there. The main idea was to get this omega over c, right? It is this condition that is making it zero, not the derivative of e. It didn't have to be sine. So does this satisfy? So if that is the case, is this a solution to wave equation? Minus plus or minus omega t. Is this a solution to wave equation? Right?
No,
No?
no, because. Wouldn't the denominator be zero?
No, it's not, right? I said.
Oh, no, that's a K now.
This is-
Yeah, you're right, you're right.
Magnitude of k is equal to magnitude of omega, but for
Yeah,
x and t, but is this a solution of wave equation? The question is it a solution of wave equation?
As long as it's in some.
As far as it satisfies them, does it satisfy? it?
Yeah, yes, as long as you have some kind of function, either sine.
But that is a function, right? 1 over that.
Yeah.
So that's a function. If you want some units, put some units in there in front, put a constant in there, and I'm saying that is a wave equation, that's a solution to wave equation. It can be any function. So any function of this kind. Is a solution to wave equation. So sine and cosines are the easiest. They have this nice wave nature to that. It's very intuitive. So we discuss that, but notice that the only condition, this is the crucial condition for wave equation. And how that comes about is that, so this is, if you notice what is happening, there is kx in the x direction plus ky in the y direction plus kz in the z direction and plus or minus omega in the t direction, correct? And the coefficients, you pick out the coefficients and you say kx square plus ky square plus kz square and because our equation has this minus sign in it, that is minus omega square over c square is equal to 0. If that is the case, remember our equation has this 3 positions and 1 time. So first of all, quiz, right? I didn't show this quiz. Show that this is
true.
this is satisfied by the wave equation. So basically, whatever I did here, take the second derivative with respect to x, take the second derivative with y, z, and t, and evaluate this and show that it is actually 0. Yes.
This would be k dot w r. If it is.
Yeah, I meant, so yeah.
X
R.
r.
Yeah, so what I do is, yeah, so R is equal to xi plus yj. That's a general coordinate, right? Sometimes I also write x. So that is you will see this going here and like I do both, right? So R is nice there because there is no confusion, but sometimes.
So in the sign, it should also be R, right?
Yes, so this should also be R. So as I said, when,
It's the same thing.
yeah. So I am using it. in
And is
favor.
that also, in that line would it be
This is
case of R?
X.
That's selected.
This is X.
Okay,
Yeah,
that's-
so
yeah,
that's
right,
the
right.
confusion, right? Yeah. Okay. So, but good point. That brought it out, yeah, okay. Okay, so notice again, so I'm pointing out, so there are there is three partial derivatives of position, one partial derivative at time, and its solution requires this. We, in the whole of electrostatics and whole of magnetostatics, we dealt with Laplacian, correct? Of phi is equal to 0. Agreed? So this was the main equation for electrostatics and magnetostatics. This says squared plus y squared plus, let's say phi of x, y, z is equal to 0. What would be the most general solution for this? This is the same idea as that.
F of k dot x. K dot
F of k dot x, that's it, right? And so this should be the any phi of the form, let's call it ax or ax plus by plus cz is a solution if, what's the condition? Is a solution if
And the constant,
huh?
what would we call like A, B, C?
Yeah.
Three,
So
A dot B,
right, a square
A squared.
plus b square
plus C.
plus c square has to be equal to 0.
C.
So that's a solution to Laplacian, right? If you can build any function like that, yes. If there are three quantities, the square of which is 0. What is A and A, B, and C? The square of three numbers is 0.
A sphere.
0.
No.
What is the question?
So the question is, if you have three numbers whose square is equal to 0, what are the numbers? Give me an
Zero.
example of
Zero.
A equal to 0, B equal to 0, C equal to 0. That's a trivial solution, right? Anything else?
Complex one.
Complex numbers, real number, there is no real solution here. Right? So it has to be complex. Very good. Right? So there are no real solutions for A, B, and C when it's a Laplacian. Unlike here you can have real solution. You have a wavelength, you have a frequency, physical quantities that you can associate. But once you get rid of the time, once you're on the Laplacian, then you're stuck with only A, B, C has to be complex quantities. But still, this is all when you have no boundaries. What we talk about is having boundary. So there are richness. Okay, so all that is going around split wave equation. The basic idea is that this equation implies that there is a wave. And a wave is anything, the actual physical motion is happening in one direction, and the mechanical, there is a momentum that is being carried over in the z direction, or I can say that the motion is confined in a certain region. It doesn't really have to be perpendicular. In an ocean wave, the particles are moving vertically, but in a sound wave, it is moving in the same direction as the wave. But either way, the particles are not moving anywhere, so they are oscillating. But the energy and momentum is, there is a flux of energy, there is a flux of momentum. You can actually move something here. Let's say at the ocean, on the beach, you can move something here, and on the other continent, they can feel it if it is sensitive enough. So that is the energy transfer. And those ideas immediately implied that there is a electromagnetic wave. Here we are talking about oscillations in electric field. And immediately after Maxwell wrote these equations, the implication was very clear that this wave exists. And within 10 years, in a lab, in one corner of the room to the other corner of the room, it was verified that this wave exists. And that led to the whole technology of radio and all of wireless communication, if you want. All of wave nature of light. So that's what we want to talk about. But this also said that there is a speed which is a universal constant, right? Which is in direct contradiction with, or in those days, it was in direct contradiction with. If there exists a speed which is universally constant,
With classical mechanics.
Newtonian.
more specifically,
Newtonian, more.
like Newtonian physics, but something in Newton. Give an example where it will go wrong.
Deterministic.
Deterministic? No, it is deterministic, so no. Like relativity, right? If you shine a flashlight, you have this two cars moving. Then there's a relative velocity. If I am moving and I observe a car that is moving with respect to me, I say that there is a velocity added to that. Galilean relativity, right? Galilean. So the Galilean relativity immediately says that velocity adds. So if I'm driving a car and I flash a light, then someone who is on the road should say that the speed of light should be speed of light plus my speed, the car speed that I'm driving. Right? Is that clear?
Yeah.
Right. So what I'm saying is that you have if you have a car. I just need one car, I suppose. So this is and I have a flashlight. That's a flashlight. Let's see.
Flashlight.
Reasonable. Okay, not a good one. Just one is sufficient. Okay, remove that.
There we go.
Okay, so that's C, and this. So someone was sitting here and shining the flashlight. So the car is moving with V, and relativistic addition will tell me that this is equal to an observer here will observe the speed of light to be C plus V, V of phi. The ground observer will say that, oh, and immediately you say that, oh, that has changed, so you know something that is going faster than speed of light, and then how do you take care of this? And the first impression was that, oh, of course, this happens. The comparison was made with sound. We have a medium. Like remember in sound what happens like Doppler effect, right? So there is an observer that moves, there is a source that moves, and there is a medium that can move. So there are three quantities that are there. But here, and the immediate generalization was that there is a medium, and vacuum was considered that medium, and there was a lot of search for that, but it turned out that there was no, it was called ether, and there was no hint of any such medium, right? And so then came Einstein, and Einstein said that for consistency, we have to look at this more carefully. So let's look at what Einstein right? Like it's very similar to this. Let's see. Okay. So if there is a source of light, and let's imagine that it is a monochromatic wave, so that there is a wavelength associated with that, but I won't be using that. Like I just need a reference, right? So that's a source of light. It radiates, right? In all direction. And if this is a position R, and this particular point reference in that wave will move at the speed of light. And what that means is that you will have R is equal to C times T. So that is a spherical wave which is moving outward at the speed of light. Right, so that is a wave.
Now I can throw a pebble into.
Yeah, so you drop a pebble, but this time you want to drop a signal, radio signal, right? So that it moves with the speed of light. Right? An antenna, yeah, but pebble is a very good example. It moves with a certain speed, mechanical speed of water that it moves with, but now this is moving with speed of light. Let's square this. And you immediately have x squared plus y squared plus v squared minus c squared is equal to 0. Right. So a circular or a spherical wave satisfies this equation. And this is being observed. So this is a phenomena that is happening. There was a source and there is a motion of a wave, and that is being observed by a frame with respect to which this source is at rest. Right, so let's call this T and X, Y, Z, right? So let's say R. So that's a frame. In this particular frame, this is being observed. Okay. But speed of light is a constant, right? For every observer, this must be true. So you come back, you take another observer, make it simple. Let's say this is moving with velocity V. And this is T and this is R. And it could be moving in the Z direction. Let's say this is Z. So that's Z change. And that is XY that is going in. So for simplicity, I have chosen this in the V direction. How will, oh, sorry, this is P prime, this is Z prime. That's your new frame. According to Maxwell's equation, in these frame, again, this is the same speed. Right, so again, it will have R prime this time is equal to C again, speed of light remains the same times T prime, which means that X prime square plus Y prime square plus Z prime square minus C square T prime square has to be equal to 0. Right, so that's the statement. Like again, notice the logic is that Maxwell showed that there exists a wave for which the speed is a universal constant. It doesn't matter who is measuring it, they will all measure the same speed. See? That means that this equation must be true for this observer, and it must be the same for the other observer too. There is no dependence on anything. Yeah,
Should those not be squared? Or half
should that
squared?
not? Yeah, but so the point was
Oh, yeah.
right. So this goes to square.
Oh,
Same
yeah,
thing.
you're right, you're right.
So this is prime square is equal to C square P prime square. So now we have two equations. And then we say, what is this transformation between this? Remember, if it was Galilean transformation. So first let's check if Galilean, right? Galilean relativity. Says that what's Galilean relativity? C prime is equal to, how is V and
VT.
VT? What's the transformation between Z prime and Z in by Galilean as given by Galilean?
VT T prime plus C.
VT, no. You mean this probably?
Yes.
Probably, yeah, that's what you said. Yeah, okay. And what's here more important? This one?
T.
just t, right? Nothing else, and y prime is equal to y. And so x prime is equal to x. Okay. And in your, so this is quiz again, right? Quiz. Show that they are not compatible. If you substitute this into this, you don't get this. Okay, so again, the quiz is to show that you start from here, substitute this in there, you do not get this, right? So that's not compatible. In your homework, you will do this at the level of Maxwell's equation itself. That's good. So the suggestion is that what else could it be? So you say that, okay, let's have this more general. Let's say that is a times z minus of b times, and we want to keep this as function of v alone, right here. A as a function of v times c minus b as a function of v and t. And should we keep the dimensions? Yeah, let's put a c here also, so that a and b come out with the same dimension. Prime c is equal to a, b, c we don't want to use because c is being used. So the e and f, e is also a function of v, c false. Is that clear? And now one would say that why are we actually restricting ourselves to linear transformation? That one can argue that if it is not linear, under these equations will not be the same if we do a translation. For example, what we expect is that if whether my equations are here or let's say I do this calculations in New York, it should be the same. Like it should not be position dependent. So if I move it around, it should not change, and that both in space and time requires that this should be linear. So very basic, simple constructions requires that you have that's a requirement. I'll stop writing V for a moment so that there is only A, B, E, and F. And the idea now is here I asked you to calculate. I should that do this, substitute this in this, and it should verify this. But now we are asking the question, what should A, B, E, and F be? So that when we substitute this into that, this is actually satisfied. So that will let us solve for A, B, E, and F. So let's substitute that. So I have x prime is x itself, y prime is y itself, plus z prime is a times z minus b times cp. Well, and minus of cp prime is e times z plus f times well. That's equal to 0 to begin with. So I substitute this in here, and I would require this to be equal to 0. But what is the condition for that? Yes, x squared plus y squared. Z squared comes from two terms. So that's a squared minus e squared times v squared, and minus of c squared d squared again comes with d squared and a minus f squared. There's also the cross terms, which is plus of minus, right? So it's minus 2vct times AV. And then the plus, so I think it is, this is plus, right? So minus is plus e times f is equal to 0. Clear?
So this is like the like a general form of how to write?
This is, okay, in general, this could have been, let's say, quadratic, for example.
So according to the Galilean unity, it's Z minus PT. So what about this one, like Z prime, is it another way to write this?
No, we are saying that we don't know what it is, like, this doesn't work. We are saying, what could this A be, like, we're keeping A, B, E, and F very general, any function. What is A, B, E, and F, which will satisfy, when I substitute this in this, I should get.
So how do you get like, so T prime is equal to EVZ plus VCT?
It is, E is, there is no B, right? This is just E, some constant,
Yeah, the function of V, something like.
function of V, yes, so any linear transformation. And probably your question is, why just linear? Right, why not quadratic, why not 1 over something?
Right. If time is relative,
That's exactly what we are going to conclude, yes. Time is going to be relative.
Okay.
Right, that is the biggest conclusion of special relativity.
so we are going to into like time's gonna change and
Time is going to change,
so.
exactly,
Then we going to substitute that and look into what happens.
and look at what happens, and it will be Lorentz transformation. So like whatever I get for E, F, A, and B is going to be Lorentz transformation, exactly. Right, I think, yeah, that's the non-trivial conclusion of special relativity, that when we are moving, our times are different. Like, we don't bother to, like, when we are going on a flight, we take our same watch and go, but if you were to go, let's say, within 2 significant digits of speed of light, within that accuracy, then your watch will not behave the same way as it behaves now. That's our understanding. Right,
Time will slow down or increase.
time will increase or decrease, will transform, that's all. And yeah, we'll come to the interpretations in the next time, I think, or maybe in the last 2 minutes or so. Yeah. Okay. Did I answer your question, or you want more clarification, sir? Okay. Yeah, okay, so if this has to be the same as that, it's clear what should be the case. A square minus E square should be equal to 1. B square minus F square should be equal to 1, and AB plus EF should be equal to 0. Right, that's 3 conditions. Like, if this has to be the same as the, right, we now have a condition AB, F. No mistake?
Shouldn't that be B square plus X square?
Is it? This has plus B square. Oh, this one you mean maybe? Right, so I think this is what it is. That's it. Right,
Yeah.
plus B square and plus F square, but there is a minus sign there, so it's plus B square, okay.
So we should change that one too. So BS squared minus FS squared is -1.
Oh, yeah, I could have done that,
Well, since you're adding the.
yeah, but now I flipped it.
I
And
understand.
CCL is
But
R
I
squared
am-
minus C squared T squared is 0.
Oh, yeah, so that is,
So now that's.
oh, so then that was a minus sign then, right? Yeah, okay, so was it a minus sign? No. That was a plus. Yeah, I could have written it as F square minus B square, I think that's what I was.
That's better.
Yeah, I think that's right.
So I think that's what I was trying to do, but then. I messed up. But, yeah, thanks for finding. And then I have F square minus B square. We have 4 unknowns, 3 equations. Can we solve for it? If we have 4 unknowns, 3 equations. Does that work?
So we can compare this with the like the first equation, right?
Yes, yeah, that's what I, so I get these 3 requirements. Right, if you have 4 unknowns, you need 4 equations to be able to solve uniquely, correct? So this is not going to give a unique answer, right? But at least we'll be able to get rid of 3 of them. Right, we will at least get some contribution, but it won't give us completely the law of response. Okay. So let's quickly do this. So let's substitute E here, right? So this implies that A square minus E, I've got to solve from here, so that is AB over F, right? And then the minus square is equal to 1. So let's take a square over F square out. A square over F square, so that's F square minus B square is equal to 1. But F square minus B square is already 1. So this implies that A is equal to plus or minus F. Or A square is equal to F square, right? That's what we can do. So A and F here, they're the same. Diagonal. Okay. Do the same thing with F square minus B square, so it is F square. Or let's put B. Reflects F, so it is AB minus AB over E square minus B square is equal to 1. So what's B square over E square maybe? Oh, B square over E square is coming out. So that's A square minus F square. F square minus B square, A over E. So E square over
E square, E square minus E square.
yeah, A square, yeah. Is equal to 1. So that says that B is equal to plus or minus. B is equal to plus or minus B, or B square is equal to B square. So that's one relation you have. That's the second relation you have. And if you put that all together, so B is equal to, so that immediately gets, so this is now an identity, right? So AB, F and E, right? So this is clearly true. Is that correct? So AB plus EF. As far as I pick the correct plus or minuses, I suppose.
Because you could say A times negative F equal to B times F, which would equal to.
I'm looking for. Okay. What we get, yeah, what we have is that, okay, so rewrite this equation now, so. E is A square minus B square is equal to 1, this first equation here. Second equation is the same because F is A, B is, so this is also the same, correct? This also leads to the same. And AB, so write everything in terms of AB, so it is this third equation will give you A, B. Plus E is plus or minus, so plus or minus of B, and F is plus or minus of A. And that's can be 0 if we choose this correctly, right? I think so. So this is not completely independent. The plus or minuses are not completely independent. So that's the choice has to be done carefully, but surely that is a solution. If one is plus and one is negative, that quickly comes up. So the main idea I want to say is that there is an A square minus B square that is equal to 0, and 1 minute. That is slow. 1 minute out. Stop. If A square minus B square is 1, can you one could think of in a single variable. This could be cosine hyperbolic theta and B could be sine hyperbolic theta. Right, so that you have parameterized in terms of a single variable. And what we are going to show is that if we have this to be equal to B over C, then we will get the Lorentz transformation. But I think at this stage we will stop and then we'll come back to this. Like we'll come back and derive the Lorentz transformation in a complete sense. Thank you.